Welcome back to the deep dive. Today, we are really putting on our thinking caps, diving straight into, well, the internal language of industrial machinery.
Mm.
We're talking electrical control circuits. These are the fundamental roadmaps. They tell electricity how to control these big motor systems safely and efficiently.
Yeah, and this deep dive is pretty crucial because we're moving past just like seeing lines on a page. We're trying to interpret the logic.
Right.
We want to figure out why a component is placed exactly where it is and what sequence of events happens if you flip a switch or maybe if the power flickers for just a second.
Okay.
And we pulled this material directly from some high-level technical training guides focusing specifically on the basics of drawings and basic circuits.
So our mission for you, the listener, is sharp, it's targeted. By the time we wrap this up, you should be able to hopefully instantly distinguish between the four main types of electrical drawings we'll cover.
Yep.
And also understand the intellectual core, that three-part engine of a classic motor stop-start circuit.
That's key.
And maybe most importantly, grasp the really serious safety implications that are built right into the control logic itself. I mean, this is kind of the shortcut to understanding the engineering behind system safety. Okay, let's unpack this.
Let's do it. So we should probably begin with the universal language of these drawings, which is the symbols.
Okay.
They exist purely for simplicity.
Mm-hmm.
I mean, can you imagine if you had to draw every single coil and every contactor to physical scale? The drawing would just be an impossible cluttered mess.
Totally unreadable.
Exactly.
Yeah.
So symbols abstract the functional component, makes it clean.
But, right away, the sources highlight this challenge that can trip up even, experienced technicians. There isn't one single, definitive, global standard for electrical symbols. You might think, okay, normally open contact looks like this everywhere. But nope. How it's drawn and even how the whole schematic is organized can change quite a bit.
Oh, absolutely. You've got different regulatory bodies essentially dictating these variations. For instance, NEMA, that's the National Electrical Manufacturers Association, sets standards used heavily in North America, especially for industrial controls.
Right. I see that a lot.
Then you've got the IEC, the International Electrotechnical Commission, which is more focused on global standards, and the IE, Institute of Electrical and Electronics Engineers, often governs broader electrical standards.
And that difference, NEMA versus IEC, that's pretty critical, isn't it? Because it affects the entire look of the schematic.
Totally.
Like the NEMA style most people probably picture, it uses those horizontal rungs. Looks exactly like a ladder, right?
That's right, yeah. The current flows horizontally, typically from line 1, L1 on the left, over to the neutral or common rail, L2 on the right. Simple enough. But then, if you encounter an IEC schematic, the sources show they're often drawn quite differently, with components placed on vertical lines. And the power source is often shown at the top. It's just a completely different visual architecture, even if it's doing the same thing logically.
Okay, so say you're handed a diagram on a job site. Maybe it's old, maybe it's from overseas, and you don't immediately recognize the style or the symbols. What's the absolute first thing you have to do before you touch anything?
Ah, the golden rule.
No?
It's non-negotiable. Always consult the legend on that specific electrical drawing.
The legend. Okay.
The legend defines the symbols used and usually identifies the standard they followed. You just never assume the components are what they appear to be based on memory. Assuming saves maybe 5 seconds.
And costs 5 hours of troubleshooting later.
Or worse.
Exactly.
Or worse. Check the legend.
Okay, so once we can read the symbols, we need to understand these 4 different types of drawings you mentioned. What I found kind of fascinating is that these 4 exist because no single diagram can really do everything, right? Like installation, maintenance, troubleshooting, planning. They all need different views.
That's the real insight, yeah. Think of these 4 views as being tailored for different people or different phases of a project. So first you got the block diagram. This is really the project manager's or maybe the system architect's view.
High level.
Purely conceptual. It shows the relationships between major systems or big pieces of equipment. Could be physical layout, hierarchy, typical flow. It tells you what is connected to what, broadly speaking. Like showing how a motor control center talks to the building alarm system.
But no wires.
Absolutely zero wiring details, just blocks and lines.
Got it. Then next.
Then you move to the wiring diagram. Now this is the installer's Bible.
Okay, boots on the ground view.
Exactly. This drawing shows the physical position of components, like on a panel backplane, and it shows the individual wires connecting to specific termination points, specific screws or terminals. This gives you that concrete, practical map for actually running the wires.
Makes sense. Number 3.
Next is the schematic diagram, often called the ladder diagram or sometimes elementary diagram. This one is the troubleshooter's best friend
Ah, okay. Why?
because the schematic completely ignores physical location. You might have the contacts of a single relay physically spread across, I don't know, 3 different junction boxes in the field.
Right.
But on the schematic, they're all grouped logically together near the relay coil symbol. It's designed purely to explain the sequence of operation. It focuses only on the functional relationships, how things work electrically.
That focus on function, not form, must be why that numbering convention on NEMA schematics is so important. The sources mention numbers on the left and right.
Yeah, exactly. The numbers on the left margin are just the rung numbers. Think of them like line numbers in a document, just for reference.
Okay.
But the numbers on the right margin, those are like the schematic's internal GPS system. If you see a relay coil labeled, say, CR1 on rung 10, the numbers to the right of that coil symbol tell you exactly which rungs you can find the contacts. The normally open or normally closed contacts controlled by that CR1 coil.
Ah, so you can instantly jump around.
Instantly track the logic, even across a really complex multi-page drawing. Super useful for troubleshooting.
Okay, that's clever. And the last type.
Finally, we have interconnection diagrams. These are about pure granular connection detail, often used for wiring between, say, large panel assemblies or connections to remote devices.
So like terminal block to terminal block.
Precisely. It focuses on specific termination points, like terminal numbers, and the exact conductor identification, maybe by color code or wire number.
Okay.
And that leads to a really critical technical point our sources stress about these, especially for multi-pin connectors or plugs. The pinout diagrams often found here.
Oh, yeah, this can be tricky.
Extremely.
Yeah.
You must recognize whether the diagram you're looking at is showing the top view that's looking at the back of the connector where the wires actually enter,
Right.
or the bottom view, which is looking at the face of the connector, the part that plugs in.
Because they're mirror images.
They are exact mirror images. If you confuse those two views, you will wire it completely backwards. You'll mirror all your connections, guaranteeing it won't work and potentially causing damage or a hazardous situation. Always, always verify the view indicated on the drawing.
Wow, okay. Good tip. So we have the maps, we understand the views. Let's move to the engine room, the heart of the control logic. The basic magnetic motor starter circuit. This seems like the foundation, right? The stop-start control you find almost everywhere.
It really is foundational.
Yeah.
And it works using 3 essential kind of interlocking sections. The whole system is designed to control a magnetic contactor coil. That coil then acts like a heavy-duty switch for the high-voltage power going to the actual motor. So the first section is the stop circuit. This has to be connected using a normally closed NC momentary contact push button.
Normally closed, meaning current flows through it unless you push it.
Correct. And its location is strategic, absolutely critical. It must be placed first in the control path, electrically speaking. That way, it can override everything else downstream and immediately de-energize the coil, stopping the motor.
Makes sense for safety.
Absolutely. And this is also where you typically find the crucial, normally closed contacts of the overload protection device. That device monitors motor current.
Right. The heater elements or electronic overloads.
Exactly. If the motor draws too much current for too long, indicating a problem, those thermal or electronic contacts open, breaking the stop circuit path, just like pushes a stop button. Motor stops instantly, preventing burnout.
Okay, so stop is NC, first in line. What's next?
Next is the start circuit. This uses a normally open no momentary contact push button.
Normally open, so no current flows unless you push it.
Correct. When you press it, it completes the path, allowing current to flow to energize the contactor coil. But crucially, as the source material points out, this start circuit must never be wired in a way that bypasses the stop circuit.
You can't wire around the safety stop.
Never. That's a fundamental violation of safe operational design.
Okay. Stop. Start. What's the third piece?
And the third piece, which is really the clever bit, is the holding circuit, sometimes called a seal-in circuit. This is what gives the control its memory, allowing the motor to keep running after you let go of the start button.
Ah, because the start button is momentary. You let go, it opens back up.
Exactly. So the holding circuit is wired in parallel with the start button, and it uses a normally open contact from the magnetic contactor coil itself. It's often labeled with the same identifier as the coil, like M for motor starter.
Okay, walk me through that. I press start.
You press the NO start button, current flows through the NC stop button through your press start button, and energizes the main contactor coil, M.
coil energizes.
Instantly, all contacts associated with that M coil change state. That includes the NOM contact used for the holding circuit. Since the coil is now energized, that NOM contact closes.
Ah, okay. So now there's a closed path through that M contact.
Right. So now you release the momentary start button, it springs back open. But the current doesn't care. It now has an alternate path through the NC stop button and then through the now closed M holding contact, keeping the M coil energized.
So the coil holds itself on bypassing the button I just released?
Precisely. That M contact maintains the flow, it holds or seals in the coil. If you want to stop it, you have to break that main path upstream, which is the job of the series connected stop button. Press stop, the coil de-energizes, the M holding contact opens, and the circuit waits for the next start command.
That's elegant. Okay, so building on that, how do you handle controlling one motor from multiple places, like that conveyor belt example, needing start-stop buttons at 3 different spots? How do you wire that safely?
It boils down to a simple rule of series versus parallel, based on the buttons function. Think about the stop buttons. Their job is to break the circuit, right?
Right. Any stop should work.
So to ensure that pressing any stop button breaks the main power path to the coil, all the stop buttons must be connected in series, like links in a chain. If you have 10 NC stop buttons in series, pressing any single one breaks the entire chain.
Okay, series for stops. Makes sense. What about starts?
Start buttons need to make the circuit to complete the path to the coil. You want any start button to be able to energize the coil.
So you wire them in parallel.
Exactly. All the NO start buttons are connected in parallel with each other. Pressing any one of them provides a path for current to flow, initially, before the holding circuit takes over.
Series stops, parallel starts. Got it.
That's the standard safe way to do multi-station control.
Okay, let's use this logic now to dig into safety a bit more. We need to talk about electrical interlocks. The sources define these basically as auxiliary contacts, either NO or NC, that are added to a circuit to either enable or prevent a specific operation.
And the key thing is, their effect depends entirely on where you place them in that circuit logic we just discussed.
The location dictates the consequence.
Absolutely. The functional placement is everything. Let's use an example from the source material, say a temperature switch contact controlled by a relay we'll call CR. Let's assume it's a normally closed contact that opens if the temperature gets too high.
Okay, NC temp switch contact. Opens on high temp. Where could we put it?
Option 1. We place that NC interlock contact in the stop circuit in series with the main stop button. What happens?
Well, if it's in the stop circuit, if the temperature gets too high, that contact opens.
Just like pressing the stop button.
Right. So it prevents the motor from starting if it's already too hot. And it will stop the motor if it's running and then overheats. Acts like an emergency stop for temperature.
Perfect. Instant safety shutoff based on temperature. Now, option 2. Take that exact same NC contact, but this time, place it only in the start circuit, in series with the start button, before the parallel holding contact branch.
Okay. So now it only affects the initial press of the start button.
Exactly. If the temperature is too high, the NC contact is open, so pressing the start button does nothing. You can't start it.
What if it's already running and then it overheats?
Good question. Once the motor is running, the holding circuit, that parallel M contact, is engaged, right? That holding circuit bypasses the start button and the temperature interlock we placed there.
So the motor keeps running even if it's overheating.
Correct. Which, depending on the application, could be a really bad outcome. It only prevents starting, doesn't provide running protection in that position.
Okay, that's a critical difference just based on placement. Is there a third spot?
Yep. Option 3, place that NC temperature contact in the holding circuit itself. So in that parallel branch in series with the M holding contact.
Interesting. What does that do?
Now, you can start the motor momentarily by pressing the start button, regardless of temperature, assuming the stop circuit is okay. Current flows through the start button to the coil.
Okay.
But for the motor to stay running after you release the start button, the holding circuit needs to work. And for the holding circuit to work, that temperature contact must be closed, meaning temp is normal.
So if the temperature is too high when you try to start, it might kick on for a split second while you hold the button, but it won't seal in.
Exactly. And if it's running normally, and then the temperature goes too high, the NC contact opens, the holding circuit breaks.
And the motor stops.
And the motor drops out. This is actually a pretty common design choice for certain types of non-critical monitoring or permissive conditions. The point is, understanding the drawing, where that interlock sits, tells you the engineer's intent for how it should function.
That placement detail is everything. Okay, this leads perfectly into the really critical safety distinction. LVR versus LVP. Low voltage release versus low voltage protection.
Right. Let's start with two-wire control. This is generally what provides LVR, low voltage release. It's typically simpler, often just using a maintained contact device like a basic switch, maybe an SPST, single pole, single throw, like a light switch. You turn it on, it stays on. Turn it off, it stays off.
Okay, simple on-off. What's the release part mean?
The release refers to what happens during a power outage. With LVR, if the power fails while the switch is on, the motor stops, obviously.
Right.
But when the power is restored, because the switch is still physically in the on position.
Motor just starts right back up again automatically.
Exactly. It's released to run again as soon as power returns. And that is extremely dangerous for many types of machinery.
I can see that. Why would anyone ever use LVR then?
It's only suitable, really, for motors that pose absolutely no hazard if they restart automatically after a power failure. Think maybe some unattended sump pumps, certain ventilation fans, maybe some types of compressors where automatic operation is expected and safe.
Okay, non-hazardous stuff.
But for genuinely dangerous machines, anything that could injure someone if it just suddenly sprang back to life. So think a table saw, a lathe, a drill press, conveyors people work near. You absolutely need LVP.
And that's where three-wire control comes in.
That's the typical three-wire manual control scheme, which provides LVP, low-voltage protection. This is the circuit we've been dissecting, the one with the start button, stop button, and that crucial holding contact.
Okay, why is that protection?
Because think about what happens during a power outage with this circuit. Power fails, the magnetic coil, M, loses energy.
Right, coil drops out.
And when the coil drops out, the M holding contact immediately opens. The circuit loses its memory. So the power comes back on even though the stop button is still closed. The start button is open because it's momentary, and the holding circuit path is also open because the M contact opened.
So there's no path for current. The motor cannot restart.
Cannot restart automatically. It is protected against restarting on power restoration. It requires a deliberate manual action someone has to physically press the start button again to re-energize the coil and reestablish the holding circuit.
That manual restart requirement is the core safety feature.
That's the essence of low-voltage protection. It mandates human intervention after a power loss for hazardous machinery.
Okay, that makes perfect sense. Now, just to round out the control elements, the sources also mention automatic pilot devices. What role do they play?
These are key components, basically sensors, that react to some kind of process variable automatically without needing a human to push a button. They automate parts of the control circuit.
So instead of a person pressing start or stop, these devices do it based on conditions.
Pretty much. Think of things like a limit switch. It detects physical position, like when a machine guard door closes or a moving part reaches its end of travel. Or a pressure switch, monitoring pressure in a tank. A float switch for liquid level control in a sump. A temperature switch, like our earlier example.
So they act like automatic inputs to the control logic.
Exactly. They often replace the manual operator input, turning what might have been an LVP circuit, if manually started, into something that operates automatically based on system conditions. Though how they integrate determines the overall safety characteristic, whether it remains LVP or effectively becomes LVR in automatic mode.
This has been a really good deep dive, actually, into the blueprint of control systems. We've sort of synthesized those 4 different views of a system, the installer's wiring diagram, the troubleshooter's schematic, and shown how that 3-part logic of the stop-start-hold circuit dictates not just how a machine operates, but fundamentally how safe it is.
Yeah, and understanding those schematics, especially the difference between LVR and LVP wiring, lets you instantly gauge the design intent behind the machine's control. You look at the drawing for a potentially dangerous machine if it's wired for simple 2-wire LVR. Big red flag. You know there's a significant risk during power fluctuations. If it's properly wired for 3-wire LVP, you know the engineer prioritized operator safety over, maybe, convenience.
Which brings us nicely to our final provocative thought for you, the listener, to chew on. We clearly established that 3-wire manual control provides LVP low-voltage protection because it requires that manual restart after power loss.
Right, the holding circuit drops out and needs a human push to re-engage.
But the sources also mention that there are 3-wire automatic control circuits. Think about controlling an air compressor automatically, cycling it between high and low pressure set points using pressure switches. That's often a 3-wire circuit with a holding contact.
It uses the same basic structure.
But it can start automatically when the pressure drops, meaning it is not providing true LVP against automatic restart after a power failure, even with 3 wires in a holding circuit.
So this raises a really critical design question for safety. If the ultimate goal for hazardous machines is LVP preventing any automatic restart after power restoration, and just counting the wires or seeing a holding contact isn't the guaranteed identifier. What is the single, non-negotiable component or type of component that must be physically included and manually operated within the circuit to ensure it qualifies as true low-voltage protection?
Something fundamental to forcing that manual input. Interesting question.